to ATS 101, Scientific Math. This course is required for the Chemical Laboratory Technology program, and it is meant to be a supplement to the ATS 115 Applied General Chemistry course. I am Diane Thomas, the director of the program and also the instructor for this course. My office is in the Norman K. Myers building on the main campus in room 223H. My phone number, 417-447-8809, and office hours are currently listed on the syllabus that is available through Blackboard. You can see those hours. If those hours do not work for you, feel free to call me anytime and set up an appointment. If you happen to be on campus and I'm in my office and available to help you, I'm happy to take drop-ins as well. Just to let you know before we start talking about the material in this course, there are no required items for this course. There's no textbook, nothing that you have to have. But some items that you might find helpful throughout the semester. Materials will be provided to you as far as literature materials. They'll either be put on Blackboard or you will be directed to look those up via the internet or in the library. But you will find it helpful to, at some point, have access, of course, to Blackboard. You have to have access to Blackboard to be accessing this PowerPoint at the moment, and to a spreadsheet program of some type, such as Microsoft Excel or any other spreadsheet program that has a statistical package that you can do some simple statistics. We will be using that to carry out statistical analyses of data later in the semester. Also, a little bit earlier on, you will find it helpful to have a scientific calculator. You are required to have one of those if you are taking ATS 115. So if you have that, you can go ahead and bring that one with you. If not, and you don't have access to one, let me know and I can let you borrow one. You do not need a graphing calculator, but if you have one, that is perfectly fine to use. Alright, in this first series of slides, we're going to just talk about the math that goes into science and the importance of understanding not only the math, but the logic to the sort of problems that you'll be working. It's very important in chemistry to think logically about problems and apply critical thinking. So when we say we want critical thinking in the course, what are we talking about? Well, one definition for critical thinking from the National Council for Excellence in Critical Thinking says that it is the intellectually disciplined process of actively and skillfully conceptualizing, applying, analyzing, synthesizing, or evaluating information that is gathered from or generated by an observation, an experience, a reflection, reasoning, or communication as a guide to belief and action. That is a very long-winded way to perhaps say that critical thinking is the art of thinking about what you're thinking while you're thinking in order to make your thinking better. It is a reflective process. It's not just taking data and reacting to it, but reflecting on what you know, how you know that, and why you know that. There are many studies that have been done on critical thinking. There are people who devote their careers to that. And one of the ways to sort of classify critical thinking is the use of higher order thinking skills based on, for instance, Bloom's taxonomy shown here. We're not going to get really in-depth in talking about that. If you want to know more, there are whole courses you can take about critical thinking. But we just want to have an idea or a concept that critical thinking is going to be that reflective process that we go through as we analyze a problem. Now, when it comes to critical thinking, perception is very important. It's how we receive information and then translate that information and experience into thought processes. Perception has a significant filtering system applied to it. Everyone has their own particular set of filters, and it defines how we think. What are our thought processes? We base our perceptions on our senses. So the things that we see, hear, feel, smell, taste, hopefully not tasting too much in chemistry, but still an important resource. So it's not only based on our senses, but our trust in our perceptions, what we perceive to be real. And you probably know that sometimes what we perceive is not necessarily reality, or it may be a series of realities. So for example, when you look at this picture, do you see one face or do you see two faces? Some people will see one person looking straight out at them with something like a candlestick in front of their face. Some people will see two faces in profile looking at one another. And some people have no trouble seeing all three of those. But what is the reality of the perception? How you perceive it will affect how you believe that picture to be. Here's another example. You may have seen a lot of these pieces of artwork on the internet, pictures of these pieces of artwork. There are a lot of people who do this sort of artwork, but this is one person in particular, Julian Bieber. He is Belgium-based. He's in Belgium. He's a British artist, and he does chalk drawings on sidewalks. Okay? They're known as trompe-l'oeil, which is French for fooling the eye. And so he will draw these so that when you are standing on a sidewalk from a certain perspective, you're going to see this almost three-dimensional appearance to the drawing. It creates the illusion of dimension. Okay? But it really, again, depends on your perspective, where you are viewing that drawing. Notice that for these two sidewalk drawings, they're both done from a particular angle, okay? And the way you're looking at it, you get that sense of three dimensions. Now, if we look at another drawing here in the next slide, we can see in the top picture that the drawing appears three-dimensional. It appears to be a globe. It looks like maybe somebody on the sidewalk at the top is standing on top of the globe. You get a very good sense of three dimensions. Now, look at the bottom picture. This is what it looks like from another perspective. If you move to the side of that drawing, then you'll see that it is not really a sphere. It's stretched out on the sidewalk in order to give that perception of three dimensions from one particular point of view. And that is something that we have to keep in mind when we're studying science and when we're looking at scientific problems, is to realize that we may be looking at them from only one point of view. So if you're ever getting stuck on something, try looking at it from another angle. Try moving to the side and see if it looks a little bit different from that direction. Okay, also some of your perceptions. You may perceive something different from other people. They might apply different filters. So for example, in this, am I reading this right? These are all real headlines that perhaps the people that wrote them were looking from a different perspective and they weren't thinking about how they would be perceived. Red tape holds up new bridge. That's some pretty good red tape. That's pretty strong tape. Typhoon rips through cemetery, hundreds dead. Man struck by lightning faces battery charge. New study of obesity looks for a larger test group. Wonder which meaning of larger they're using there. Astronaut takes blame for gas in spacecraft, so on and so forth. So you can see that depending on how you are reading this and what filter you're using, you may see it differently than someone else. And by the way, don't include your children in the batter when you're baking the cookies. So, but a very good activity to do with your kids. So what are the major components of critical thinking? Well, as we said, logic. We want to apply logic to a situation. We're going to think like Sherlock Holmes. Okay, so what did Sherlock Holmes do? Well, he used deductive reasoning. He looked at the facts. What do we know as a certainty? What can we validify? Use sound arguments and sound conclusions. Okay, so he wanted nothing but fact and certainty. But there is another method of reasoning, with logic. You can have inductive reasoning, where you have a diversity of facts. You're not looking at a certainty, but you're looking at a probability. What is the most probable factor? You look at generalizations. So what do we generally know to be true? And we look at hypotheses. So with hypotheses, if you remember your scientific method, they're not necessarily foolproof, but it's just a way of explaining the body of data that we currently have. That doesn't mean that it can't be disproven, but it's just working with what we know. So we have to look at it from both deductive and inductive logic. So when you look at logic problems, you've probably seen a lot of these out on the internet. They're kind of fun brain games, but they really are good for developing logical thought. So even if you think of it as playing games, it's really good brain exercise. So for example, the classic one, Mary's mom has 4 children. Okay, the oldest one was called April, then the next one was May, and the third one is June. So what is the name of the 4th child? Well, if you don't stop and apply your logic to it, you start looking at the pattern. And the pattern is April, May, June. Well, of course the 4th one should be July, right? Well, no. We said in the first sentence that Mary's mom has 4 children. We just named 3 of them, April, May, and June, so the 4th one has to be Mary. Or the one where a man and his son are flying across the Atlantic, and the man asks the flight attendant if his son can have a look inside the cockpit, if he can go see what's going on at the front of the plane. Okay, the boy goes to the front of the plane, the pilot lets him come in, explains about the plane and the controls, and when the boy leaves to go back to his seat, the pilot turns to the co-pilot and says, "That was my son." But we just said that this boy was sitting with his dad in the back of the plane, so how can that be? Well, the temptation is to think of pilots as only being male, but could be a female pilot. It could be that the pilot is the boy's mother or other parent. So we have to apply logic. If one thing doesn't hold, what else can we use to explain that? Okay, so logic is going to be very useful to us in problem solving. We always want to think logically. Okay? And then in problem solving, we want to apply a certain set of techniques. So the first thing we have to do is understand the problem that we're being asked. We have to read it carefully, heed what it's telling us, be sure that we truly understand the question that is being asked of us. We need to identify what do we know, what do we want to know, what do we not know, what's the relationship between those two. We generate a strategy, and we'll be talking about that more in this course, and if you're taking the ATS 115 chemistry, we'll talk about it in there as well. Once we have a strategy for how we're going to solve the problem, then we apply what we know to it, solve for it. We think about the answer. Does the answer make sense? And if it does, we're probably okay. If not, we will repeat, we'll modify our strategy and repeat if necessary until we can solve a problem. Okay, so just some thoughts about problem solving and critical thinking. Now the other thing we want to talk about here is just to start to lay some groundwork for what it is we'll be doing in the chemistry course. And you will see that there are overlap in the courses. Sometimes one course will get ahead of the other. Just be aware that in this course, what we're trying to do is go more in-depth into the issues that a lot of first-year chemistry students have with the math and the problem solving. So just be aware that you may be seeing some of this in duplicate. Okay? But, alright, so the metric system. What we need before we begin looking at mathematical problems in chemistry is to know what is the basis for that. Because in chemistry, we never have just pure numbers. We always have numbers with units attached to them. So for example, if I told you to go to the store and get me 3, you'd probably look at me like I was a little bit crazy. 3 what? There are thousands of things in a store. Okay? But if I said, go get me 3 sodas, or go get me 3 gallons of milk, okay? That's a unit. That is a number of something and an item with it. So in chemistry, every time you write a number, you're also going to have a unit attached, and those units will be in the metric system. So the metric system is an internationally agreed decimal system of measurement. It has been agreed the world over that this will be the standard for measurement. It is used almost everywhere in the world by everyone, but certainly by every scientist in the world. This was originally based on the meter, and my French is awful, so I apologize for my pronunciation, but the mètre des archives and the kilogramme des archives. So in other words, the archive of the meter and the archive of the kilogram. These are actual standard physical items that were used as the basis for the measurement of a meter and a kilogram. And this has actually been around for a few hundred years. It was introduced by the First French Republic in the year 1799. Now, over the years, the definitions of the meter and the kilogram have been refined so that they are not dependent upon a physical item. So for example, the kilogram, this was a measure that was kept under very secure, air-free conditions to try to keep it from degrading, but it's a physical object, and no matter what we do, every time it gets handled, every time something happens to the system, it's going to degrade a little. The mass is going to change. And so they've redefined it so that it's not dependent upon that item sitting in a museum somewhere. Same thing for the meter. And the metric system has been extended to incorporate many more units than just a meter and a kilogram. Those were originally the only two units. The term that is now often used for the metric system is the SI system, or the International System of Units, and the SI is based from the French for it. It is the official system of measurement, as I said, in almost every country in the world. Okay. Now, it was officially sanctioned for use in the U.S. in 1866, and there have been various movements to push for adoption of that in the U.S., but it's never really taken hold. But it puts us really behind in the rest of the world. If you look at this globe right here, at this map, you'll see the countries in green are those that officially use the metric system. The only countries that have not adopted the metric system are the United States, Burma, and Liberia. Okay, so we've got Burma over here in Asia, and Liberia right here on the west coast of Africa. And those are very tiny countries. Certainly we're the only major industrialized country that does not use the metric system. So just some food for thought there, but keep in mind that in chemistry we will be using the metric system. Okay, now the metric system, as we said, is based on a decimal system. So why this decimal system? Well, if we don't use this decimal system and we want to make a measurement in the English imperial system, these things listed here, and I certainly won't read all these are all units that you can have in the English imperial system. So length, area, volume, mass, force, pressure, look at all the ones for pressure, energy, power, temperature. Okay, temperature at least is simple, degrees Fahrenheit, but look at how many different units there are. And in temperature, degrees Fahrenheit, that is what we call a relative scale. It's relative to something else. It's not an absolute. So again, there are issues with using that sort of a system. Okay, now compare all of these to the metric system. If you want to measure that same range of the same quantities in the metric system, these are your units. For length, you've got meter. For area, it's a square meter. Volume, cubic meter. Mass is a gram. Force is a Newton. Pressure is a Pascal. Energy is a joule. Power is a watt. Temperature is Kelvin. Okay, now you'll see some things in parentheses here. So for instance, for area, square meter, and I apologize, that should say area, A-R-E-A, it just says A-R-E. The area of something is squared meters. Volume can be a cubic meter. It can also be defined as a liter, but a liter and a cubic meter are the same thing. Mass, grams tend to be very small, so there's also a metric ton that is just a sizing up of the gram, and it is different from the imperial ton. We'll talk more about that at another lecture. Temperature, Kelvin is an absolute scale, but we also use degrees Celsius, which is a relative scale. And we'll be talking more about the difference of those when we get to temperatures. Now, those are the base units for any measurement you want to make in the metric system. Much simpler. You only have to remember a few. If you want greater or smaller quantities than those base units, 1 through 9, then what you're going to do is base it on the decimal system, and you're going to combine it with a prefix, such as micro, milli, centi, deci, deca, hecto, kilo, and mega. Okay, so ask yourself, which set of units is going to be easier to remember, because you can't always refer back to a sheet. Do you want to remember that English system, or do you like the metric system? I think if you think about it, you can see why most scientists decided the metric system was the way to go. Okay, now those prefixes. As I said, use a system of prefixes. Those were just a few that you saw. Here's a little bit more complete list of all of those. And you have versions of this in your chemistry book as well. You can find these online at any time. But notice the nice thing about these prefixes, it's just a multiple of 10. So here's our base unit right here in the center. We start at 1. If we want to multiply up by 10, then we use the prefix deca. Multiply by 100, we have the prefix hecto. Multiply by 1,000, here's kilo, so on and so forth. Okay, and some of these, of course, get used more often than others. Now, it used to be, 20 years ago, you probably wouldn't have heard much beyond mega. Kilo and mega were the big ones. But now, there's some other prefixes, giga, tera. These are probably looking a little bit familiar to you. And if you think about it, the reason why those are familiar is because of computer memory now. We talk about computer memory and flash drives and storage in terms of gigabytes and terabytes now, and we're even getting into the petabytes. So we're getting into these very large numbers, and you can see how those multiply up. Okay, now there are exponentials and then scientific notation for those. We'll be talking about exponentials and scientific notation in the next lecture. Now, if we need very small numbers, we can divide by series of 10. If I divide the base unit by 10, I get deci. I divide by 100, I get centi. That one probably looks familiar. If you think about a cent, we talk about a penny as being a cent. A penny is 1/100th of a dollar. So we divided by 100. So centi, there's that prefix. If we divide by 1,000, we get milli. Divide by, keep going. You've got micro, nano, pico, femto, so on and so forth. Okay, now, generally speaking, in chemistry, you'll see some micro and nano, but generally from here, milli, and then up to kilo. So the first 3 here and the first 3 of the division will be the ones that you see the most. Okay, so from milli up to kilo. That's what you'll be looking at, and really you need to know those. Okay. Now, how do those work with the units? We use them just as place values. So if we have our base units, let's say we want to measure distance in meters, so that's the abbreviation for meter right here, M, mass in grams, volume in liters. Here's my base units. If I am getting into smaller numbers, I'm dividing by 10 each time. Okay, so I put a D for deci. Here, if I divide by 100, I put a C for centi. I divide by 1,000, I put an M for milli. If I'm going to multiply up, okay, if I multiply by 10, I have to, now I've already used D for deci when I divided by 10. So to multiply by 10, I use DK as my prefix. So decameter, decagram, decaliter. Okay. And generally speaking, you won't see deca a lot or deci. If you're multiplying or dividing by 10, we usually just put it in terms of the number. We would say 10 meters rather than 1 decameter. Okay. If you are multiplying by 100, hecto, again, we don't tend to use hecto a lot. We tend to say 100 meters, 100 grams. But certainly that prefix is there, is available. When you start getting into the thousands, that's where you see people really start to use the prefix. So if I multiply by 1,000, I have a kilometer, a kilogram, a kiloliter. Okay. All right, so let's look at those base units really quick, just to give a sense for what those are, the sizing of those. So you're used to seeing rulers that probably have inches and millimeters on them. So the meter, as we said, is the measure of length or distance. If I have something that's about 1 millimeter on one of these rulers, that's the distance between any two of these little dark lines on the ruler. That's about the thickness of a dime. That's not very thick. Now, 1 centimeter. A centimeter is 10 millimeters, so if I count out 10 of these lines, sorry, my cursor keeps disappearing. Okay, so for instance, if I started at 1 and went to 2, 10 millimeters is going to give me 1 centimeter. That's about the width, not the length, but the width this way across a large paperclip, one of those bigger ones. That's about a centimeter. Or it's about the distance across your fingernail, depending on how big your hands are. A meter is about the width of a doorway. It's about 3 feet, 39 inches is what you get. Okay. Now, I multiply it by 1,000, a kilometer, a kilometer, that's about 6 city blocks or about 10 football fields. There are about 1.6 kilometers in 1 mile. The gram is used to measure mass, and we measure mass on Earth in terms of weight. So when we put something on a balance, we say it weighs a certain amount. What we're doing is determining the mass of that object, the amount of stuff in that object based on gravitational pull. So how much is that? Well, 1 gram is about the mass of 1 small paperclip. If I took 1 paperclip and put it on a balance, I'd get about a 1 gram mass. A milligram, that's about as much mass as you get in a single little grain of table salt. So if you took your shaker and poured out 1 little cube of salt, then that's going to be about a milligram. Okay? Now again, take that with a grain of salt, because again, as I say, that's table salt. It's a fairly standard size. If you tend to use kosher salt or sea salt, bigger pieces, that's going to be a little bit bigger than a milligram. And a kilogram is about 2.2 pounds, which would weigh about as much as 6 regular apples from the grocery store. So just to give you an idea of estimating of that. All right, so next we'll look at volume. Volume, our base unit, is a liter. Okay, so, and we're usually measuring the volume of a liquid or a gas, but certainly you can use a liter to measure the volume of anything. If you're measuring volumes of solids, that's typically, remember we said something about a cubic meter, you would tend to use cubic meters, cubic centimeters for the volume of solids, but for liquids or gases, we tend to say liters. All right, so you know a liter, so if you know a 2-liter soda, 1 liter base unit is half that bottle. You can have all these different volumes. So a 20 ounce is a little over 500 milliliters. I believe this one right here is a 1-liter bottle. So you've got a 2-liter bottle, a 1-liter bottle, 20 ounces. So now we go back to that imperial system, but if you look on your labels, you will see that milliliters are listed on those labels as well. A milliliter is going to be about the amount in a drop of something. Like if you use a medicine dropper, or when you get into the lab, when you're using Pasteur pipettes or disposable plastic pipettes, then you're going to see a drop is about a milliliter, okay, depending on what you're using. And then you have kiloliters. Okay? You don't hear that one too much, but a kiloliter would be the volume of about 500 bottles of 2-liter bottles of soda. Okay, so I don't know if you've ever seen or heard the classic case of the gentleman who found the Sundrop soda on sale for, I think it was 64 cents, something like that, in the grocery store, and he bought out the entirety of what they had. He really liked Sundrop soda. And there had been all sorts of wonderful math and science problems that had been built around this particular case. So we might have to throw one of those in later, but that's a lot of soda. Okay, so you need to be proficient in changing those metric units, in going from a base unit to kilometers, from kilometers to millimeters, or whatever, from grams to kilograms, any of those. You need to be able to move up and down that scale simply by multiplying or dividing by some power of 10. So as we said, if you want to go from a larger unit to a smaller unit, You're going to be multiplying by a factor. If you want to change from smaller to larger, you're going to need to divide. Okay. Now, you could memorize the chart, you could memorize all those numbers, and eventually that is pretty much what you'll do, but there's ways to help with that, to kind of help you remember what you're seeing there. So for example, if I look at those 6 that I said, so we have the kilo, the hecto, and the deca that are multiplying up. We have deci, centi, and milli going down. We can put them in terms of what is known as the metric staircase. So if I draw a set of stairs where every step is one of these prefixes and then a base unit right here, I'm going to put my base unit in the middle, and then I have 3 steps, 1, 2, 3 above my base step, and then I'm going to put 3, 1, 2, 3 below. And you can put as many steps as you want, but again, we're going from the more commonly used kilo down to milli. And I apologize, I think the milli is missing an L in there as well. A better explanation of that, let's take a look at this. There's a mnemonic that you can use to help you remember what goes on each step of the stairs and how to use it. There are several of these out there, but the one that I like is kangaroo helps dingo because dingo can't multiply. So kilo, hecto, deca, base unit, deci, centi, and milli. Okay, so what is this about kangaroos and dingoes? Let's take a look at somebody explaining. Now I do apologize, this came from a 6th grade science and math school, but again, this applies for us as well. It's just something really good to know, so let's take a look.
Alright, in this video we're going to be reviewing the metric system and how to convert between units within the system. Alright, when we use the metric system, we have a really helpful tool called the metric staircase. And in order to remember how to draw the metric staircase, we made up this silly sentence. It goes like this. Kangaroo helps dingo because dingo can't multiply. Now it's pretty ridiculous, but it's really useful because it tells us how many steps to draw and what the labels for each step are. So let's go ahead and get started here. Kangaroo helps dingo because dingo can't multiply. Once again, we can fill in these steps with the letter. Kangaroo helps dingo because dingo can't multiply. Now, just for 6th grade math this year, there's only a few that we need to worry about. We want to focus on the K step. K stands for kilo. We're going to be using this step quite a lot. Another one you're going to see a lot of is all the way down here at the bottom. The M stands for milli. Occasionally we're going to use the C step, which stands for centi. And the most important part is to recognize the B step. B stands for base, and in the metric system we're going to be talking about 3 different bases. The first base is for mass, so if you want to measure the mass of something, we're going to be using the base gram. For volume, when you measure liquid, our base is liter. And then for distance or length, our base unit is meter. These can be abbreviated. For gram, you'll see just a little g. For liter, a capital L. And for meter, a little m. Depending on what prefix is in front of it, kilo, centi, or milli, we'll know how large it is in comparison to the other units. Alright, let's do a little bit of practice. We're going to start out looking at what units we have. Say we have 5 grams of something, and we want to know how many milligrams that is. Well, I'm going to start out on my gram step. Well, I don't see a G on here, but I do know that gram is a base. We got it right here. Gram is a base unit for mass, so I'm going to start on my base step. And this time I want to go to milligrams. Well, my prefix for milligrams is milli, so I'm going to move my way down to the milli step. It takes 1, 2, 3 steps to get there. So that's going to tell me how many times to move my decimal. So if I have the whole number 5, where's the decimal at? Well, it's right behind it. Here we go. And I want to move it how many steps? 1, 2, 3 steps. We moved down the stairs toward the right. So I'm going to do the same thing with that decimal. 1, 2, and 3. So my decimal is now right here. Let's fill in those empty spots. So we know that 5 grams is equal to 5,000 milligrams. You'll notice 5,000 is 1,000 times larger than 5. and so it takes 1,000 milligrams to fit in a gram. The nice thing about the metric staircase is it works right along with our number system. So we know that when we move a place 1, for example, we're at 5 and we move the decimal over 1, 5 to 50, well, we just made it 10 times bigger. If we move the decimal again, that's another 10 times. So 10 times bigger, 100 times bigger. If we move it one more time, times 10 again, that gets us 1,000 times bigger. So when we move one step, we're making it 10 times bigger. Times 10 again makes it 100 times bigger. Times 10 again makes it 1,000 times bigger. In this one, our unit is 20 meters, and we want to change it to kilometers. So we're going to start on our meter step. Be careful, you don't just choose M, because M step really stands for milli, and we're not talking about milli. If we were talking about milli, it'd be MM for millimeters. We're just talking about meters, and we know that meters is our base, so we're actually going to start on the B step. B for base. We want to make it up to kilometers, so here we go. 1, 2, 3 steps. So I'm going to start with my whole number here. 20 decimals at the end. I am moving 3 steps, but this time I'm moving to the left. Notice as I go up the steps, we're moving to the left. So we're going to move that decimal 1, 2, 3 times. There's my decimal. Fill in that hole with a 0. So it looks like we have 2 hundredths of a kilometer. Alright? In this example, we have 15 meters, and we want to change it to centimeters. What step are we starting on? Well, M stands for meter. We know that meter is a base. Starting on my base step, and I am moving to centimeters. So here we go. 1 step, 2 steps lands me at centimeters. I move my decimal twice. So in the whole number 15, moving that decimal 2 times to the right, because as we go down the stairs, we're moving to the right. 1, 2, fill in the empty holes. So 15 meters is equal to 1,500 centimeters. In this example, we have 4 kilograms. We want to know how many grams that's equal to. Let's go ahead and start out on our kilogram step. We want to go to our gram step, which is the base. So that takes 1, 2, 3 steps to get there. Starting out with 4, it's a whole number, decimals at the end. We're moving that decimal 3 steps to the right, because as we go down the stairs, it's going to the right. 1, 2, 3. Fill in those holes with 0, and it looks like 4 grams is equal to 4,000 grams, which makes sense because we know that kilo is 1,000 times larger than the gram, and so it takes 1,000 grams to make 1 kilogram. Well, if it takes 1,000 grams to make 1 kilogram, it would take 4,000 grams to make 4 kilograms. Take a look at this one. We have 12 kilometers, and I want to know how many millimeters that is. Well, what step should we start on? Well, kilo for kilometer, and we want to make it all the way down to milli, because we have millimeters. So let's see how many steps that takes. 1, 2, 3, 4, 5, 6. Start out with my whole number 12. I'm moving that decimal 6 times to the right, so 1, 2, 3, 4, 5, 6. Fill in all of those empty spaces with zeros, and we got a pretty big number here, guys. We got 12, 0, 0, 0, 0, 0, 0, which happens to be 12 million millimeters. So there's a whole lot of millimeters in a kilometer. Let's take a look at one more example. For this one, we have 2.5 liters is equal to how many milliliters? Let's look at where we're starting. We're going to start with liters. Well, I don't have an L on here, but I do know that liters is the base for volume. So I'm going to start on my base step, and I want to move to milliliters. So I'm going to have to go down those steps. 1, 2, 3. Here we are. So if I have 2.5, this one already has the decimal in place, so all I have to do is move it. Here we go. 1, 2, 3. Fill in those empty holes with 0, so it looks like we have 2,500 milliliter.
Okay, so hopefully that helps you to see how to use that system and why we need to use the metric system for science. So if we hadn't started with the English system, we always use the metric system. There are cases where, it might not have been quite as neat. Say, mister, that's a pretty nice 37.9 liter hat you got there. So there's a case where maybe using the metric system isn't easier, but in most cases you'll find it's a lot easier than using the English system. Okay, so that wraps up the first lecture for scientific math. And we will be doing some practice with this on Friday. We'll be doing some worksheets, testing that out. And next week we are going to take a look at scientific notation and logarithmic scales.